Thank you everyone for coming to my presentation. Today I will present you my last 4 years work of PhD. To be honest, it was looking almost more like a maze, and sometimes I ended up to the dead ends, but I had two of my supervisors, George and Thomas, that they were guiding me through this journey. I'm almost close to finish, and now it's time to I have this chance to be evaluated my works by these honorable researchers, and hopefully this will end up to my degree. So mainly I was working with micro aerial vehicles, and these platforms are widely used in different applications for inspections, such as airplanes, offshore structures, power lines, nuclear plants, and wind turbines. Also, due to their agility and capabilities, there is a DARPA subterranean challenge that one of the goals is to deploy micro aerial vehicles in tunnel, urban, and cave environments and do the exploration and navigation, which I will go more in detail about that in upcoming part of my presentation. At the beginning of my PhD, I was mainly looking for coverage path planning. So if we have a structure that we want to inspect, how we can do the inspection. The method I was working on is guaranteed to have some overlapping for visual inspection areas. Also, I identified branches of infrastructures and guaranteeing full coverage of the infrastructure while supporting multiple micro aerial vehicles. And I should highlight that one of our goals in our lab is to demonstrate the capabilities of aerial robots in the field test. So for this case also, we evaluated in the outdoor environment and real life scenarios. Assume that we have a looking forward camera with the aperture angle of alpha, and we have a structure that we want to inspect, and we can define the safety distance of omega. Then our goal is to inspect it in the horizontal planes, and then we go up and then inspect the next horizontal plane. In this case, we define this lambdas is actually these horizontal planes, and then we define the beta term, which is the overlapping term. When the beta goes to infinity means you have maximum overlapping, and when beta is 1 means that minimum overlap. So what we do is that we start intersecting the planes with the model that we have, for example, here wind turbine, and we extract the points that we have. So this almost going to be what we expect to look like. However, we don't know how many branches we have and which one is correspond to where. So we do clustering, and actually we find also the center of the clusters. This information later will be used to provide the heading commands for the micro aerial vehicles. So then we guarantee that we are always looking to the structure, and then we can assign these different branches to different agents too. And we did a simulation of the inspection of wind turbine. It means that we import the CAD model of the wind turbine. Then we do an inspection with 1, 2, and 3 from left to right. And as expected, we also reduce the flight time of the mission. And here I should highlight that time our platform actually had the flight time of 10 minutes. So actually it was infeasible to do it with one pass, with one agent, the whole inspection of the wind turbine. And that was it needed to have this multi-agent support in our algorithm. Then we move to the outdoor. I wish it was not a virtual meeting today and you could be here. I show you the around of the LTU and also provide you some demos. But this is one of the statues we have in LTU. So here, as you can see, this is the horizontal planes we inspect. We go to the next one, we do another inspection. And that time we had only one platform. So we did the test twice. We overlay the videos together. And actually, no, the left one is like recognizable that it's an overlay image. The two image bottom is the online stream from the camera. And the red dot is actually used for localization, which was not the scope of this presentation and PhD, and I will not go deeply into it. One of the output of this type of missions is the extraction of the 3D reconstruction of the environment. This later can be used for fault detection or doing the maintenance. Also, I was telling you that our main goal is to do field tests, and my main vision was to do the inspection of wind turbines. So we visited one of the wind farms in Sweden, and we inspect the area, the same concept that we provide the paths that inspect the base and the blade. So, and here you can see that we are inspecting the base at beginning with one agent. We have a bit of more oscillation, and this is due to the wind gust. As we expect, these areas has a high wind gust, so there is more wind gust that we have. And then we go to the next plane, and then we do another inspection of the horizontal plane. If I go a bit further for the video, here you can see the case of two of them for the base inspection, and also a bit further you can see the inspection of the also blade. The output of this inspection, we can summarize it to like some of these plots that you can see. The left is the base, the right is the blade. And one thing that is interesting, and we can see it in the pictures, that the higher we go, the higher that the error of the following the path is increases. So the error of trajectory and reference increases. And this is due to the higher wind gust, the higher we go. I should also highlight here that this work also received a recognition from Swedish Royal Academy of Engineering. So I want to show you some of the onboard images. So I was saying that I was guaranteed to looking always toward the object and the full coverage, but in reality, I noticed that due to disturbances such as wind gust, sometimes we are looking to the areas that we are not expecting. And this was not considered in our framework. This actually gave me a motivation and inspiration to consider camera footprint in the coverage problem. I relaxed the problem, so instead of having the camera looking forward, I assumed to have a camera looking down and do the 2D coverage. So in case of we have no orientations and we are perpendicular to the target area, the red rectangle is the expected area to see. However, we have usually roll, pitch, or yaw, like attitudes, and this can result to this trapezoid area. This is actually, as we see, there is a big difference in the area that we cover, and I thought that maybe it will be nice to consider it in a 2D coverage. So what I did is that I consider formulation for considering camera footprint for the coverage problem in order to maximize the coverage and minimize the number of camera footprints. And I evaluated in the lab environment on the convex and non-convex areas. So we assume we have a region of omega that we want to inspect. We have set of rectangles that are distinguished by their centers and their orientations, and they have a fixed width and length, because as I'm going to do assumption that I'm going to have a constant altitude. So we want to find the positions and orientation of these rectangles to cover this area of omega. And after we find the positions of them, we are going to pass through center of each of them in order to cover the area. And we assume that while we are passing through one rectangle to the next one, we provide enough overlapping between frames that can later be used for the image stitching. So A, we can assume A is the function that finds the area of the polygons. P is the union of rectangles. We find the union of rectangles intersection with the target area, and this area of this area subtracted by the target area should go to 0 in order to maximize the coverage. We can have also second term that is minimizing the number of rectangles. However, this term can be omitted because roughly we can estimate how many rectangles we need for the target area by dividing the total area by the area of the rectangle. And we have positions of rectangles and also orientation. And we evaluated in 2 non-convex shapes, as you can see here in the lab environment. And as an outcome, we noticed that we managed to reduce the length of the path compared to the grid-based method significantly. And this actually maybe can be later used with the more degree of freedom for the camera, and I mean, like higher degree camera movements and coverage path planning. Then I noticed that most of the time I have this error between waypoints and my trajectory, and I decided to move toward the nonlinear model predictive control for macro navigations. I wanted to have the controller that can be used in a constraint environment, consider uncertainty in localization, which is one of the main limitations in real-life scenarios, and actually also have a 2D and 3D obstacle avoidance integrated. And again, we evaluate it in the multiple experiment and simulation environments. So this is the real footage from underground mine. If I add a bit of illumination, we can have different scenarios. Usually we have uneven surfaces, dust, obstacles, and this actually give us the motivation to have some controller that consider these uncertainties and also have collision avoidance. Additionally, LTU Robotics is part of the CoStar team, with other members of MIT, Caltech, and JPL, and we are participating in the DARPA Subterranean Challenge. And I should highlight that we won in February. We won the second stage of the competition, which was a subterranean environment, and that was also another motivation for me to have this type of controllers to be used in a competition. And to give you the architecture of the problem, so assume we have a high-level planner that provides waypoints. The NMPC, based on these reference points and estimated offsets and variances of the measurements and obstacle information, provide thrust, roll, pitch commands for low-level controller, and low-level controller provide motor commands for our UAV. Also, from the point clouds 2D or 3D, we can extract the obstacle information. Our NMPC formulation is almost typical, and most of them. So we have a term to track the positions error. We have a term to have it for hovering. So it means that we want to have a gravitational acceleration and zero roll and pitch. And also we have a term delta U to reduce the aggressiveness of control actions. And each term has their own weight, Qx, Qu, Q delta U, which shows the importance of each term. Assume that we have a set of variances of measurements. Then we find the probability of these variances, and then we use it in the Shannon entropy, which means that if the probability goes high, the Shannon entropy goes towards 0, and then we are not going to track that specific term. This gives us the opportunity actually to track positions or velocity or none of them based on the uncertainty we have in localization. And instead of maybe drifting or terminating the mission, we can maybe continue the mission and hope for the reaching to the more rich area feature with the features that give us a better localization information. And then we have this obstacle avoidance part. In the left is in case of 2D, and the right is a 3D case. Let's assume the DS is the safety distance we want to have. In the case of 2D, I assume to have 5 obstacles: front, back, left, right, and up. And these are like a walls. And also, I'm going to consider the kinematic of these walls based on the movement of our micro air vehicles. Means that if we are going forward, it actually means that the wall is coming toward us. So that's the term that I add here. So to predict the wall movements. And also for the 3D case, we extract the plane equations and then find our distance to these planes. What we add extra here is this term, which means that we translate the UAV is always in the center of the point cloud, which make these two terms decouple from the localization information. So even if uncertainty increases, they still can have these two active. And then we evaluate the method in one of our homemade platforms that is developed specifically for navigation in underground mines. It has LED bars for the looking forward camera, LED bar for looking down optical flow, and 2 one-beam lidars that we have for finding the distance from wall and ceiling and ground. We did a test in underground mine. Here I should highlight that I don't consider localization uncertainty. We are commanding the UAV to fixed altitude and going forward, and we just having the velocities as estimation. The yellow dots is actually the point clouds and then the blue arrow is the heading commands that I will go to discuss it in more detail in the next part of my presentation. And as you can see, we are avoiding the obstacles and keeping distance to all walls. Then we evaluate our method in the blockage area. So we are giving the same altitude 1 meter and command the UAV to go forward. The UAV goes up because of the blockage. We don't hit the ceiling. After it reaches to the end, we, as an operator, command it to return, and the same procedure continues. So the UAV return, keep a safety distance to the obstacles, and coming back to operate. Then we wanted to evaluate the collision avoidance in the case of 3D. So we moved to Gazebo. We equipped our platform with the Velodyne. And again, here we don't consider uncertainties localization. And mainly we navigate with different velocities in this confined environment to be sure that we are satisfying the constraints. Also, I should highlight that intentionally we put some waypoints close to the walls to violate the constraints and see the performance of the method. In all cases, our method avoid collision, keep the safety distance from all walls, and also we compared with the potential field method, and we noticed that due to the large number of the points, the tuning is quite hard, and also potential field has more oscillations and sometimes violate the constraints. Next part, the same structure, but this time we start adding the uncertainty in localization. So these red dots actually is the information for the position that we are giving to the UAV. We still have the constraints active, so we still avoid the walls and we don't violate the constraints, but due to the uncertainty in localization and fixed weight for the NMPC, we have a bit of oscillation. And next part, we do the same test. So we ask to the UAV to stay in one position, but add the noise to the measurements. But instead, now we have these adaptive weights. As you can see, we have a bit less oscillation. And this is the part that we think that maybe this helps us to continue the mission until this uncertainty reduces. Next part of my thesis, I was working to deploy them macro vehicles in underground mines. And mainly I was looking for the baseline solution for this technology to be used in the mine. What is the minimum sensors or hardware we need to send and consider them as a scouting platform. Also, due to the harsh environment, I was considering mainly two approaches, one LiDAR-based and one vision-based, and to find open areas. And finally, also I evaluated extensively each method in the multiple field tests. And so underground mines, there are some limitations, as I said, low illumination, uneven surfaces. And this is the one footage from our camera. And when we have a dust, it can be noisy like that, or also give us the blur effect because of the dust. So we want to have these platforms integrated in the production areas, but also we want them to consider as a fast deploying unit that can be considered as a consumable and can be replaced immediately. So we assume to have something like a tunnel, and we want to always look at the center of the tunnel to avoid the collisions and inspect the whole area. To give you the architecture that we use is that we have a potential field that use the ranges to find the velocity references for the NMPC. Here, due to uncertainties in the position, so we propose the concept of floating object, means that the NMPC going to use altitude, velocities in X and Y, Z, and roll and pitch as a states. And then this provides the control input for low level and the same approach as before. And also we have this heading generator part that based on the ranges or images provide heading rate commands for the UAV to look at the open areas. initially, I was looking to the geometric-based approach. So we know the ranges, we know their angles. If we sum 3 of them, that is one that looking left, right, or center, we can find the direction toward the largest actually B. And then based on proportional controller, we can send it as a heading rate command to our microradar vehicles. And here you can see the video of it. In this video, mainly the blue arrow should be observed. The problem that I see here is that we had these S movements. That is, one is because of the low reliable range of the 2D LiDAR that we had that moment, that was I think 4 meters. And another one is that I noticed that only relying on 3 beams is not robust enough because sometimes you have a wet surfaces and you think it's open, but it's actually not open area. So what I did next step is that I consider weighted arithmetic mean for finding the open areas. So the idea is that you find the sum of ranges multiplied by their angles and then divided by sum of ranges, and this will be the open area. Also, we do one step more. We integrate it with the IMU measurement. So it means that we know what is the current heading we have. We know the angular velocity of our platform, and then we can predict what it will be. With the compulsory filter, we can find the desired heading, and we send it with the proportional controller to our UAV. Here is the simulation, experiment that we did. Again, you can look at the blue arrow, and as a result, we have smoother actions. We don't have any S-shaped movements because we robustified with more ranges actually, and actually integrated with the IMU. And we noticed that we always look at the open areas, and it's better than the previous method. Then I came with the idea is that, do we really need the 2D LiDAR? What if I have just flying cameras and just remove the 2D LiDAR and find the open areas with the camera? So initially I was looking to some computer vision methods like contour detection. So assume we have this as an onboard image. Then we can binarize it based on the level of illumination. We can find the contours and we can find the center of it. And when we find the center, we can normalize it and map it to the range of the heading that we want to send, which is, in our case, we assume to have -0.2 and 0.2 radian per second. Here you can see the video footage of our experiment. You can look at the left, actually, which is the darkest area that we are extracting. I should highlight that we did one assumption here. We assumed that the environment is dark enough and the tunnel is actually the darkest environment. So it will fail when there is a external illumination except the microradar vehicle that we have, because then the darkest area will not be the tunnel access. And this gave me the motivation that maybe I need to do something more. So I consider convolutional neural networks. So what I did is that I collect some data from forward and left and right walls and train my network to give me the classification of that. If the image is that we are getting, is it the left wall, right wall, or center? And I'm going to give discrete actions, control actions for each category. Here you can see the test flight that we did. So we noticed that we are having a bit more heading oscillation, or let's say frequency of control action, and this is mainly due to this binary classification, because a bit of rotation give you the other direction of the ball and results to the different direction of the heading commands. Also, we evaluated with the different level of illumination. For example, these two left ones are quite identical from our eyes, but it gives enough information for the CNN to provide the correct heading commands. And also, we evaluate the method with the different velocities of the platform from 0.2 meter to 1.2 meter to just be sure that the method is fast enough. Then, due to this bang control, which actually expected, I moved toward regression approaches for finding the heading. And the problem is that underground mines is very hard to get access, and there is a very little data. And CNNs or deep learning methods, most of them, they need high amount of data sets for training. So what we did here is that we assumed to have an onboard image. We extract the pseudo depth map of the environment. We did the k-means, and then we find the deepest part of the image, and this is actually the information that we are looking for. And after we did these centered extractions, we trained our CNN in the offline approach, and then we evaluated in the online method to provide us the heading rate comments. So you can see here our navigation, the extracted centroid in the onboard image, and as expected, we have a smoother control actions compared to the classifications, and it looks a bit more promising. However, I think there is a lot of room to improvement. For example, if we have junctions, how to consider them, or if we have a void areas. So to sum up, I was proposing algorithms for inspection of the complex structure with multiple micro vehicles. I consider camera footprints for 2D coverage, unifying the NMPC approach for considering pose uncertainty and collision constraints, and proposing scouting micro vehicles for underground tunnel navigation. And all of my PhD last 4 years was resulted to 8 journals and 23 accepted conferences. And as a future work, I would like to highlight that I want to take 2 directions. One is the theoretical contribution, which I will call it a SLAP, SMAP, and a SLAM. Means that when we are doing path planning, we should consider uncertainties in mapping and localization and find a path that robustify these 2 terms, and same for localization and mapping part. And maybe at the end goal, we will have some unified theoretical framework that do the real simultaneous localization, mapping, and path planning. To give some example, assume fx is the term, for example, for localization, j is the term for the controller. Then we have a multi-objective optimization that should consider system constraints, closure constraints, localization constraints, and communication constraints in case of multiple of platforms. So we can have a team of micro vehicles that individually they improve their own localization and mapping, they improve their teams and also other teams. And also I would like to have some applications and move towards space hybrid area scouting, that they autonomously explore of subsurface voids for planetary exploration, and some collaborative task accomplishment like maintenance or load lifting. And I think there is a need of having high-level mission planner such as fleet manager to define the proper task for each of these platforms. Thank you for your attention. I would like to conclude my presentation.